One thing we have not seen at all in this class thus far is any inequalities involving functions. We are going to see that now. We're going to look at both polynomial inequalities and rational inequalities. Let's start by looking at polynomial inequalities. A polynomial inequality is a polynomial equation where the equal sign has been replaced by a less than, greater than, less than or equal, or a greater than or equal to. I am sure you have seen inequalities up to this point where we have had a less than, greater than, less than or equal, or greater than or equal. What's different here is that we want to focus on how do you deal with that when it's in a polynomial, or with a polynomial. We're going to start with a little bit of motivation here. This is a parabola. The function is given here, f of x equals -4 plus 5x minus x squared. That negative on the x squared makes it an upside down parabola from our study of quadratics. We want to know where this function is actually equal to 0. This is a little hard to see. The y-axis is here at 0, and so we want to know where the function, or where y is 0. Well, remember, that's at these x-intercepts. So f of x equals 0 when x is equal to 1, or when x is equal to 4. That answers the first question. Then it wants to know where is f of x. I'm actually going to do this in a different color so we can kind of keep it all straight. F of x is less than 0 when, what I'm really asking you to find there is what values of x make the y less than 0. F of x is like the y, right? It's the output of the function. Y values less than 0 would be anything below the x-axis. So we're talking about here and here would all be situations where y is less than 0. So that happens when x is less than 1 or x is greater than 4. Now let's talk about when f of x is greater than 0. And in that situation, we are talking about the y values being bigger than 0. That's any of this part of the graph, right? All of these y values here represent y values bigger than 0. So we have f of x, or the function, greater than 0 when x is between 1 and 4. I wanted to look at that picture to sort of help us motivate how do we solve a polynomial inequality. Notice that this function only changes from positive to negative, or from negative to positive, from red to green, or from green to red at the x-intercepts, or the zeros of the function, right? Those blue dots is where it changes from red to green or green to red. So we need to find those, because that's where we could make a change from positive to negative or vice versa. First thing we have to do is we have to rewrite our inequality so that we have a 0 on one side of the inequality. This also could have an equal sign underneath, of course, depending upon what you were given. First, we want to solve f of x equals 0. That helps us find the zeros. It helps us find these blue dots. Once we have those blue dots, those zeros, we know that the function can only change from positive to negative or negative to positive at those exact points. So we draw a number line that sort of represents the x-axis, and we plot those zeros, and that breaks our x-axis up into intervals. And we just test a point in each of those intervals. We are going to plug the value, that test value, into the function. If we get a positive, the function will be positive on that interval. If you get a negative, the function is negative on that interval. And then we want to know, which do we want? We want to know, do we want the function to be negative or do we want the function to be positive? Let's take a look at what I mean through an example here. We'll kind of work through these. First step we have here is we have to make sure we have 0 on one side of the inequality. We do have that. Then we take whatever the function is. In this case it's this. X minus 5 times 2x minus 5 times 3 minus x, and set it equal to 0. This one's already factored, so we can set the factors equal to 0. If it's not, you will need to factor it, either using old techniques that we have or the new techniques that we learned in the last couple of videos ago for solving, finding zeros of a polynomial. We have these 3 values. Let's graph, or put those on a number line. From smallest to largest, 5/2 is actually 2.5, so that's going to be the smallest. And then will come 3, and then 5 will be over here. Those are the places, if we were to graph this, that this function would hit the x-axis. That breaks this into 4 different intervals. -∞ to 5/2, 5/2 to 3, 3 to 5, and then 5 to infinity. We are going to make some test points in each of those intervals. TP, test points. Test points, unlike the pandemic inability to find TP toilet paper, we can always find test points. Let's pick a number in this interval. I think an easy one is 0. It's between, it's less than 5/2, so that's good. You could pick -1,000,000 if you wanted. It just has to be in that interval. This one's a little harder because something between 2.5 and 3. Let's go with like 2 3/4. I would go with 4 in between 3 and 5, and then maybe 10 out here. 10 is usually pretty easy to calculate. I want to plug those test points into the function. So sometimes I will write f of TP, f of the test point. I want to plug the 0 in. When it comes to plugging the 0 in, I don't actually care what the number, the actual number is. I only care if the result is positive or negative. So I'm going to think about, if this is my function here, right? When I plug 0 in, this first factor is a negative number. I have 0 minus 5 is -5. The second number, when I plug 0 in, I get -5, a negative number. Last, when I plug 0 in, I get a positive number. The reason I don't particularly care about what that number is because I know that whatever it is, it's a negative number times a negative number times a positive number, which gives me a positive. Let's do the same thing with the 2 3/4. This technique of not really caring what the number is particularly helpful in a situation like this where we have a yucky number. When you plug 2 3/4 into that first factor, you get a negative. Then, when we multiply by 2 and subtract 5, we are going to get a positive number if we do 2 times 3/4 and subtract 5. I know that because it's bigger than the 5/2, which is what would make that 0. So something bigger than that is going to make it positive. When I plug 2 3/4 into the 3 minus x, I will also get a positive. A negative times a positive is negative. And we continue with this. Plugging in the 4, we have a negative times a positive times a negative, which gives me a positive. Plugging in the 10, I have a positive, and a negative. 3 minus 10 is negative. So that's negative. That tells me a little bit about this graph, actually. It tells me that on negative infinity to 5/2, the graph is positive, so it is above the x-axis. Then between 5/2 and 3, it's negative, so it dips below the x-axis for just that short little window. Then between 3 and 5, it goes back up. So I'm getting a picture like this, and obviously this is not exact, but you know, something kind of like this, right? I'm going up here. What I want to know is, where is this function greater than 0? Meaning I want positives. Well, that is here and here. So my answer is negative infinity to 5/2 union 3/5. Any x values in between those two will give you a positive number for this function. It asks us to graph the solution on a real number line. I'm going to draw an open circle here, and here, and here. I'm using an open circle because I don't have an equal sign on that. It's just strictly greater than. So I do not want to include the points where it's equal to 0. But I do want to include the values between 3 and 5, and I do want to include the values less than 5/2. And that's it. That's how we solve a polynomial inequality. This one is similar question. The problem here is that we don't have 0 on one side of the inequality, so we have to start by subtracting 3x. X cubed plus 2x squared minus 3x less than 0. So now less than or equal to 0. Now I'm looking for negative numbers, right? I want to know where the function is less than or equal to 0. Let's focus on factoring this. I hope this factors. Let's call this f of x that we're working on here. And that will be x times, it does factor, x plus 3 times x minus 1. When I set that equal to 0, I will get x equals 0, x equals negative 3, and x equals 1. So let's put those on a number line. Negative 3 is the smallest, 0, and 1. Let's pick some test points. Negative 4, negative 1, 1/2, and maybe 10. You could pick negative 10 over here too if you want. I like my factored form of this better than the original that I have here. I really like to use this one because then I can do my positive and negative trick. When I plug the negative 4 into x, I get a negative. I get a negative for the next one and a negative here. So a negative times a negative times a negative is negative. Negative 1 plugged in gives me a negative, a positive, Negative 1 minus 1 is negative, so I get a positive there. Positive 1/2 gives me a positive, and a negative. So the product of a positive, and a negative is negative. And then for 10, it's positive, positive, positive. So all positives there. Remember, this interval is negative infinity to negative 3. This is negative 3 to 0. This is 0 to 1 and 1 to infinity. So we just tested each of those intervals. In this case, I want negatives. I want my function to be less than or equal to 0. So my solution is going to include these negative intervals. I'll just write this. Negative infinity to negative 3, union 0 to 1. Is that correct? Not quite. Those intervals are where it's negative. I want to know where it's negative or equal to 0. So I need to include these values where it's equal to 0. So I have to do a bracket on negative 3. I want to include the negative 3. I want to include the 0. I want to include the 1. Everything in between 0 and 1, and everything below here. So I need brackets instead of parentheses here to include the values where it's equal to 0. Okay, that's our polynomial inequalities. We can do a similar thing with rational inequalities, but there's one little extra thing. Because that's a little extra nuance, I'm going to stop the video and we'll do a separate video for rational inequalities.